All right, let's see. Any questions over the homework? Joshua! Okay, never mind. Hey, anytime. Anybody else have any questions? Loic. Oh, I always do that. Number 3, was there a particular part?
The second part, so confirming sex by confirming by showing the y is actually.
Trying to look at my work and figure out where I did that. Show that. Oh, it's wait. I have to remember what the problem says. Show that f of t is a solution to that. Sketch 4 solutions. The slope will confirm this by showing. So where did I actually do that? Oh, down there. Okay. Finally found it in my work. So show that this is the general solution. So we have this. We want to show that this is the general solution. So what did I do? I don't even know. Looks like I took the derivative. So I did that. Took the derivative. And then it's like, oh, yeah. Okay, I see what I did. So if this is y and then dy dt is this, does that make sense? Because we have f of t right above. So the derivative of f of t is just 1/2, and then the derivative of this term would be that. And then I just plugged into this. So this would be the derivative, and then I plugged f of t into that part, and then just showed that you get the same thing on both sides. Any other questions? Yes, 3. Yes. Because remember, the negative is not squared. And so, like, the only way for this to be 0 would be if time is 0. What do we have here? This is the only bad thing about doing these solutions years ago. Is y of t a solution? So this is why. So we got to put all this together. So if it was a solution, that would mean that we would have a horizontal line. But if you start where t is 0, like there's no place where you have a horizontal line. So that's why. Any other questions? Can I have your homework then? And I don't really have a reality check today, because I was like, not much to put into a reality check, except for like one order method problem. So I'll roll that into the next reality check. Don't you worry. Oh. I don't want you I mean, wait, no. Thank you. And that means we're going to jump right into notes. Yeah. Oh, yay, indeed. I'm going to make you guys think today on the notes, too. Ha, 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 ha. All right. There is the topic for today. We're going to look at the logistic differential equation and its solution, which is just the logistic equation. So let's first look at the logistic
differential equation. We're going to start with this. So the logistic differential equation is a differential equation. So it looks like this. dy dt equals ky times 1 minus y over a. So let's kind of examine this thing a little bit. So this actually represents logistic growth, which we're going to look at what that means. If you might have seen it in biology, because it's usually used in that kind of setting, but it can be used in other settings. But A is called the carrying capacity. And K is a positive constant. Godzilla. So let's look at a graph that would be modeled by this. So all the action's really going to be happening in quadrant 1. I'm going to put a little bit of room to show something in quadrant 4. But here's the idea. Oh, that's supposed to be a different color. There we go. Imagine this line right here, this horizontal line, at y equals a. So, like I said, a is the carrying capacity. So you start with some population. So at time equals 0, you have some population present. Then the population will begin to grow exponentially, but as it approaches the carrying capacity of the environment is going to limit that. So it's not going to continue to grow without bounds. It's going to start being limited. So it starts to grow exponentially. Oops, I can't do that and hold it down. And it starts to approach the carrying capacity. Now, in the real world, obviously, this population probably hovers around the carrying capacity. It may go a little above, something then limits it, brings it down below, it grows again. But theoretically, that's what the model says, is that this is what would happen with the population. If the population is already bigger than the carrying capacity, so if the population starts above the carrying capacity, then it's going to decrease in number until it approaches the carrying capacity. And this typically doesn't happen because usually we're using this in a contextual context where having a negative population doesn't make sense. But theoretically, we can plug negative values into y here. So if you do start, for whatever reason, in the negative values, this would just continue to grow in the negative direction. But like I said, that's usually just in the context of the problem, gibberish. Usually doesn't even make sense to consider that. So there we go. And if we take a look, let's kind of compare the equation with the graph. So let's use purple. If y is close to a, let's look at what happens on the equation. So when y is close to a, when y is close to a, this fraction becomes close to 1, and then 1 minus 1 becomes close to 0, and when you multiply by ky, you're close to 0. Your derivative is close to 0. Your rate of growth is close to 0. So when y is close to 0, or close to a, your slope is close to 0. And you can see that's exactly what's happening on the graph. As y gets close to a and it starts to approach the carrying capacity, the slope of the function becomes 0, close to 0. Same thing from above, it'll come close to 0. So that part makes sense. That seems to flow both from the equation and the graph. So if y is close to a, the slope is close to 0. And if y is relatively small, and positive, let's look at what happens to dy dt. So if y is relatively small, this fraction y over a is close to 0, which means 1 minus that fraction is close to 1, which means dy dt is close to ky. So it basically is dy dt equals ky. And I don't know if that differential equation looks at all familiar to you guys, but this is exponential growth. That's our differential equation that represents exponential growth, which makes sense in context of the problem. So when y is close to 0 and positive, we're talking close to the initial population. And so, yeah, it's going to grow at an exponential rate initially. So as you're close to the y-axis. So it seems to match, seems to follow. So any questions on that? This will be a formula to memorize. It will come in handy. But I wonder how we solve this. Oh, yes, look.
Can it also be negative and also equal to y?
Yeah, and so then that would be the exponential decay. That's what's, if you think about it, it's going to force it to grow negatively. Grow, anyway, do that.
But wouldn't the factor still be positive?
The factor, what factor are you talking about?
Like what in the equation would be negative? Is 1 minus basically 0. Right?
But if we start in the negative direction, remember we're saying relatively small, but it's still negative. It's not actually 0. So it's this term. It's this factor here. That would make it negative.
Right, okay.
So what I want you guys to do right now, I'm going to go ahead and just pull this problem up. I want you guys to try to solve it. It's not the easiest differential equation to solve, so we'll look at it together. And there's actually different ways that you'll see the solution written. We'll talk about that. But what your goal is, like I'm telling you what the answer is right now. When you solve that differential equation, it should look like that. So see if you can figure out how to solve this and make y look like that. That is your quest. Have fun. And for people watching at home, why don't you try it too? Pause the video now. I'll scroll up a little because I see some people still writing, so let me know, is this too far? Another little tiny thing that I saw a few people doing, it's like, oh my God, now you're getting there, yeah, but then this part right here, when you're going to integrate this, don't forget about, since it's minus y on the bottom, that makes that a minus sign outside. Yes, Joshua. Second step from the bottom, like this one? So way up here? So what I did was I multiplied, I'll write it out. I multiplied top and bottom of the integrand by a. Oh, you see it? Okay. I just wanted to get rid of that complex fraction. Yes? Oh, yep. We don't need an ln, do we? It's optional, right? Just kidding. Woo! Look at that. I'll scroll up a little bit more. Let me know if that's too far. Too far? Ooh, tell me is that good? Oh. No, I don't remember where I was. Is this okay? It's fun, isn't it? And it's one of those where, like, you get to a point, you're like, well, how do I know? Is this good enough? And actually, I mean, there's nothing to say that different parts weren't good enough. Because once you get here, it's like, well, I solved for y. What's wrong with this way? Really, there's nothing wrong with this way. It's just not typically written this way, which is why I gave you something to shoot for. So. What? Ace. Ace! Look at that! Yeah! This is one of those, if you want practice with like differential equations and partial fraction decomposition and stuff, even though you see it once, it's still good practice to go back and try again. But now, if you compare this to what we were trying to get, one of the things was there was only supposed to be an a in the numerator. So we can divide top and bottom then. If we divide top and bottom by
CE to the KT, then the numerator just becomes that. Each one of these terms divides by CE to the KT. So we have CE to the negative KT. The C has now changed values, different constant.
And then we're basically there. Yes, Joshua. The 1 over a. Just cut off on the top. Oh, actually, let me go back up one more. Oh, actually, I have to go back a little bit. Look on the right-hand side with the partial fractions. So, actually, I'm going to go back a little further. So, since my two constants that I was trying to get in the numerators, they were both 1 over a, I basically factored out that 1 over a and then just made them the numerators 1. So since b and c end up both being 1 over a, I factored out the 1 over a and put it in front. Does that make sense? You're welcome. All right. Any other questions getting to that point? So there's actually, depending on which book you use or who you're talking to, there's actually 2 typical ways that this equation is written. This is one of them. And actually, normally I would just stop there and say, let's just learn this one. But your textbook will actually use a different one. So if you go back and look in your textbook and stuff, I don't think it really affects doing the problems. But if you happen to go back and use your textbook as a reference, I didn't want you to get messed up. So these are 2 different ways. They're still equivalent. It's just the C is a different thing, and we're going to look at the C in a little more detail. But this term right here, they both have this e to the negative kt in it. It's just there's this C or negative 1 over C. Positive C is an arbitrary constant. Negative 1 over C is also an arbitrary constant. They're just 2 different arbitrary constants. And there are 2 different ways of writing it. I think this way is a little more typical, and I think you can see why. It's just nicer. But there is this version also out there. But you'll see when we do a problem, it doesn't matter which one you use, it all still works out. Anybody need this? We're going to kind of summarize everything now. Actually, no, not yet. Almost. Yes. So, since to go from this step to this step, this one I will just show a different color. Where is it? This line. So if I divide the top and the bottom by
CE to the KT, this term is 1 over CE to the KT, which I just made the exponent negative.
All right, so let's actually look at both versions and what the value of C is in both of them, because you will also want to memorize what C represents. So I just have them both here. Let's just look at it. So you can write this down if you want, but we're going to put it all together, like summarize it. But C, to find a value of C, we're going to base it on the initial population, which I'm representing as y sub 0. So looking at this first version, the one with the 1 plus in the denominator. So if we let t equal 0, then we're talking about the initial time, and we want to solve for C. So I just took this original equation and let time equal 0. But at time equals 0, you have your initial population. That's why y becomes y naught. Why not? I don't know. And if t is 0, then e to the 0 is just 1. So you wind up with just 1 plus c at the bottom. And then if you go through and solve this for c, you get this for c. And then version 2, if you do the same thing, you almost get the same thing for c. But remember, the difference between version 1 and version 2, that arbitrary constant was either c or negative 1 over c, negative reciprocal. That's the difference between these two c's. Pick one and use it. Do not try to use both. I don't care which one you guys use. Just pick one and go with it, and let that be the one you memorize, because you can see how easy it is to get these things mixed up. That's why normally I would just go with one, but this particular book likes version 2 that I think is stupid. Yeah! Anyway. So does that make sense how to get the C's? See? So the next thing, I got all three of these things summarized. We put the differential equation and these two logistic growth equations together. And then, like I said, you pick which version you want. I see some people writing this down, so I'm going to let them finish. Turns out these equations, like, we've done a lot of difficult stuff with them, but when we actually use them, oh, that part's easy. Yay. Anybody still need this? Okay, so here we go. If you want it all together, you can write down whatever you want, but there's the logistic differential equation that we had already mentioned at the beginning. And remember, A represents the carrying capacity throughout all of this. And then there's version 1 and version 2. When you memorize version 1 or version 2, memorize the C along with it. That will be very helpful. But you can see that it's not hard to derive the C. So if you're not, memorizing isn't your strength, at least memorize how to get it, and then you can always derive it quickly. But it definitely makes your life easier if you memorize C. Personally, I screw them up every time because they're so similar, so from year to year, I end up deriving C. Clouds within clouds. Plans within plans. Dune, good movie. Anybody watching Boba Fett? It's good. It's different, but it's good. If you're looking for like a lot of action, you're not going to get it. But it's still really good. You got a lot of backstory, and I don't know, I'm really enjoying it. And Ming-Na Wen, God, I love her. I want to hang out with her. She's pretty cool. Do you realize that she is 58 years old? Ming-Na Wen is, she's a Chinese actress. You've probably seen her in stuff. If you ever watched Agents of S.H.I.E.L.D., she was Agent May in that. She's been in a lot of other stuff, though. If you looked up her name, you'd be like, oh yeah, I totally recognize her face. Yeah, right? What? Yeah. She's got moves. She can kick some butt, and she looks fantastic. And she's 58 years old. Did I mention she's 58? I was reading an article about her. This just makes me so happy. In high school, apparently she was the president of the science fiction club. That just makes me so happy that, like, somebody like her, she's so awesome. Yeah. Anyway. All right. I got another quest for you guys. And then we'll look at, like, an actual application of this problem. Anybody still need this, though? Alrighty. So here's what I want you to do right now. Find the point of inflection. And tell me what it means. In general, how do you find a point of inflection? Second derivative. Look for a sign change in the second derivative. You already know the first derivative. No, you already know the dy dt that I already get. That's the logistic equation. That's the derivative of the logistic equation. So, yeah, take the derivative of that, find where the sign change is, and then talk to me. Tell me about it. I shall pause the recording now. Hey, people watching the recording that weren't here in class. Look at this part right here. Change it in your notes. It was a over y, but now it's y over a. Okay, I'm going to pause the recording and go back to the other one. So, factoring out the dy dt is what got me there. Use this so people on the video can see. And that left me with this, which, nicely, I also had like terms. And then I could have done this in the beginning, but honestly, I just didn't see it until now. There's also a k that I could factor out. So I factored out that extra k. And then it became easy. Because at this point now, you just set each factor equal to 0. So in general, if you already know that you're going to have to factor something, do what you can to not multiply it out. And in that second step, because of this plus sign in the middle, I would have had to multiply it out if I didn't have common factors. But thankfully, I had common factors. So I could start factoring right from the beginning. And then once you set each factor equal to 0, you get this. Yay! Yeah, we're not done yet. Because now we have to just say what this means. What does this mean? And actually, have we found the point? I mean, there's 3 points of inflection then?
No, maybe.
Maybe, it could be. Or could there be? I mean, we know what a point, go ahead, Sid.
So, wait, so for y equals 0, like, we don't have negative values of y, right?
Right.
So,
Yeah, let's actually, to kind of help us, let's go back to the graph and also look at where these values for y would be on the graph. So we got y equals 0, y equals a over 2. Anybody still need this, though, before I go back to the graph? All right. So if I go back to the graph, oh, where is the graph? There's the graph. So remember, it's not that all three of these happen at once. It's just depending on what your initial value for y is, you get one of these three curves. But if y equals 0, we didn't actually do that. If y equals 0, what happens? Yeah, well, if y is 0, yeah, that's 0. We actually, I mean, if your population is 0 to begin with, it's not going to grow, it's not going to decay, it's going to stay 0. So it ends up just being this horizontal line here. You don't have a point of inflection there. So that's extraneous. Or you could say it's out of the domain if you think of this as representing population. You're not going to have a population of 0. If y equals a, you are at the carrying capacity. You're just, again, going to be a horizontal line. Again, there's no point of inflection there. There's nothing happening. The point of inflection is at a over 2, half of a, which on the graph, just eyeballing it, would be something like that. That would be where y is a over 2. And then we can see that there definitely is a change in concavity there. So we do have an inflection point. So could we put this, if we think of this as representing population growth, can we put a meaning to that inflection point? Can you describe the slope at that point? Like, relatively speaking to the rest of the graph? Yeah? Exactly. At the point of inflection, the slope is at a maximum. The slope represents the rate of growth. So when the population reaches half of the carrying capacity, that's when the rate of growth is maximized. And that's the meaning behind the point of inflection. So I'm going to write that down. If I can find where the problem is. Right there. So when y equals half of the carrying capacity, the rate of growth of the population is at the maximum. Boom, boom, boom. So any questions on that? All right, last problem. This is going to be a word problem. You can write down as much or as little of this word problem as you want, but I want you to work out the word problem. Does anybody need this still before I go to the word problem? And this will be our last problem. But there's 3 parts to it, so, you know. Can't believe February seems right around the corner. Have you already figured out how you're going to spend Groundhog Day? Who's going to get up at like 3 in the morning and watch a live stream of? You bet you. I am. Yeah. My brother and sister and I did it last year. We got up and watched the live stream of it. It was great. So great. I'm so bummed though. Do you know what they did? And my brother and I, my sister's not, she just humors me and my brother. But they, if only I'd known. So because you know, they had to do the whole Groundhog Day virtually last year. So they sent out a thing saying you could send in a picture of yourself and they would make a cardboard cutout of you. And, you know, you could attend virtually like that. My brother and I were going to do it. We just never got around. Oh my God! When we saw the live stream and we saw the cardboard cutouts on the field there, we were so bummed. They're not doing cardboard cutout. I think they're actually doing a live thing this year. So bummed. Oh Yes.
You explained to Brian what you were thinking with Groundhog Day? Because he wasn't there. He wasn't here.
Groundhog Day is like, I'm going to leave the recording on. So you can jump ahead if you want to, but Groundhog Day is the best day of the year. So every February 2nd in Punxsutawney, Pennsylvania, they have this Groundhog Day celebration. And, I mean, they go all out. I went 2 years ago with my brother and sister. They estimate there were about 40,000 people that went. So we all gathered on this field called Gobbler's Knob. And they have this whole big ceremony. They have these guys, they're called the Inner Circle. And they have their tuxedos and top hats. And they come out. And they and there's on stage, there's a stump. Because that's where Punxsutawney Phil is, the groundhog. They have this whole big ceremony, and they read this proclamation. Well, actually, no, wait, sorry, I take it back. So they lay out this red kind of fabric on top of the stump, and they reach inside the stump, and they pull out Punxsutawney Phil, and they put him on the stump, and then they put 2 scrolls in front of him. And he speaks in Groundhogese to the president of the Inner Circle. He's the only one. He has a magic cane that allows him to understand Groundhogese, so he's the only one that can speak to him. So Phil will tell the president of the Inner Circle which scroll to pick. He picks the scroll, he reads it, and either Punxsutawney, I'm going to mix this up. He either sees his shadow, which means that there will be 6 more weeks of winter, or he doesn't see his shadow, which means spring will come early. Or it's vice versa, but I think it's that way. And so he predicts the weather every year. February 2nd, he predicts the weather. And in case you're wondering, like this has been going on, I think it's over 160 years. And yes, it's the same groundhog, because every year they also give Phil the magic elixir, which prolongs his life by another 7 years. And so as long as he gets the magic elixir, he will never die. Unfortunately, Phil is monogamous, though. There is a Mrs. Phil, in case you were wondering. But the magic elixir doesn't work on her, so Phil has had to watch several of his wives die. It's sad. But it is the same Phil every year. It is the best thing, so yes. Anyway, I'm sure you've all had enough time to write this down, so here is your last problem. Like I said, write down as much of it as you want, but this is what you need to work on. And again, I'm going to pause the video. Let's just see the start of the solution. Let's see, so... So I went ahead, by the way, and I worked it out both ways, depending on which version of the formula you used. But you can see your end result is the same. That's why it doesn't matter which one you use. So the blue version is using one of the versions of the formula. The green one uses a different version. So I still have to solve for K, but that at least gives me C. So any questions getting to that point? Other hints? You want me to keep going? You want to know what K is? A little bit more. So there's K right there. Now this is what I'm talking about. K is this ugly decimal, and on the AP they're going to expect that you don't round until the very end. So you can either, when you're typing in the formula to use later, you can either type in, that K is the natural log of 487 over 1287 divided by -5, or just store this decimal in your calculator. I stored it into one of the variables and then referred to it later. Kim, yeah. No 1 plus 99. Oh, I multiplied over here, so I distributed the 104 into both terms. Sid.
For B, we get it like a decimal. Is that like round down?
Was B asking about the number of elk? You can round down or round up. I think I rounded up because it was 0.5 something, so I decided, yeah. But yeah, either one. And in fact, if I remember, anyway, was it 629 or something like that? I mean, you might even see like about 630 elk if you want round to that. So just all depends. So any questions on finding K or, oh, yes, Kieran. Can do what? Oh, yeah. You want all parts, right? There's... Anybody still need the solution to part A? I think he's done with that. Oops. There's part A. Part A. Sorry, Karen, were you still looking at the problems? Okay. What? Solve in terms of... Yeah. I think she's done. Okay. Oh, got it. Got it. Here are B and C. So yeah, in case you missed it, the discussion about like what do you round to? There's nothing set in stone. It really just depends on the application and what makes more sense. So if it was a multiple choice question, they would not give you both 628 and 629. That would just be mean. So that's the last that'll make you think today. Any questions about that? I'm going to go ahead and stop the recording again.